To us, the universe seems steady. Drop a stone, it falls. Turn off the light, darkness follows. Everything obeys a rhythm, a law, a reason. Or so we thought. In the outer space where we don't know matter stops behaving like matter, particles flicker between existence and absence, slipping through barriers as if they were never there. One moment here, the next everywhere. And the strangest part, when we try to watch, everything changes. This isn't imagination or myth. It's the foundation of modern physics, a mystery that left Einstein, restless Bohr, fascinated and Schrödinger haunted. So breathe slowly. Let the noise of certainty fade. We're about to step inside the paradox, the quiet place where the universe stops making sense. Once the universe appeared orderly like a perfect clock, its gears clicking in harmony with time. Every motion, every fall, every orbit could be predicted, traced and trusted. We built our confidence on that rhythm. Newton's laws ruled like scripture. Einstein refined them with the curvature of space-time. Cause led to effect and the cosmos obeyed. Now take a breath and step with me into that past. We stand beside Isaac Newton beneath an apple tree, the fruit hanging motionless for a moment before gravity claims it. He watches, and for him the world makes sense. Everything has a place, a reason, a chain of command. If we know the position of every atom, he would say we could foresee the future as clearly as the ticking of a pendulum. But imagine how small that vision was, like trying to describe an ocean by measuring a single drop. For centuries, this mechanical view comforted us. Planets moved in ellipses like dancers bound by invisible strings. The sun burned at the center, steady, unchanging, a celestial lighthouse. On Earth, machines mimicked that perfection. The human mind felt it could master the heavens themselves. And yet beneath this confidence, something began to whisper. Light, when examined closely, refused to behave like a tidy wave or a neat particle. It shimmered between both as if undecided. Electrons slipped from their orbits like ghosts. The atom once imagined as a miniature solar system turned out to be mostly emptiness, its solidity only an illusion. You and I are standing now inside that illusion in a world where the table beneath your hand is 99.9999% empty space. Between the nucleus of each atom and its electrons yawns a gulf so vast that scaled up a single atom would be a stadium, and its nucleus a grain of dust hovering at the center. Everything solid, everything reliable is mostly nothing. What does it mean to live in a universe built of absence? We can still drop an apple and it will fall. We can still send a spacecraft to Saturn and it will arrive within seconds of prediction. The equations work. But beneath them, at the smallest scales, the rules unravel. It's as if reality hides a second layer, a trembling foundation where certainty dissolves. Physicists began to peer into that depth, and the deeper they looked, the less sense it made. The photon, one tiny packet of light, can act as though it has passed through two paths at once. The electron can spin both clockwise and counterclockwise until we decide to look. The cosmos still moves, but its mechanism hums in whispers rather than clicks. We have left Newton's orchard behind. Now we float inside a field of probabilities, a realm where position and motion are only suggestions. This is the threshold of quantum mechanics, the place where reality ceases to be a solid wall and becomes a shimmering fog of possibilities. We believed that knowing enough would mean knowing everything. If we could measure a system, its position, its speed, its energy, we could predict what it would do next. That was the promise of classical physics. But as we entered the subatomic world, the promise fractured. Even with perfect information, nature refuses to be precise. Imagine you are standing before a beam of light in a dark laboratory. A single photon travels toward a thin metal plate carved with two slits. You expect the photon to choose left or right, like a marble rolling down one path. Yet when it strikes the screen behind, the pattern that emerges is not one of particles, but of waves, ripples of interference, as if each photon has passed through both slits at the same time, and then you measure it. The moment a detector is placed to observe which slit the photon takes, the interference vanishes. The photon chooses. Reality collapses from many possibilities into one. This is the heart of the measurement problem, the point where physics itself stares into the mirror and cannot say what it sees. Before measurement, the world exists as a wave of probabilities, what we call the wave function, denoted by the Greek letter psi, pronounced psi. It describes everything the system could be. But when we look, PS collapses. The infinite becomes finite. The possible becomes actual. Why? No one knows. You can feel the unease in every conversation between scientists. Some say the wave function is merely a tool, a convenient calculation, not a real thing. Others insist it is physical, a field that shivers across reality. Yet all agree the act of observation changes the outcome. It is as if the universe hesitates until we pay attention. Let's scale this strangeness to something you can hold. Imagine tossing a coin. Classical intuition says it will land heads or tails depending on spin and air resistance. But at the quantum scale, the coin doesn't spin through the air, it spins through possibility. It is both heads and tails until it meets your gaze. If a single electron behaved like that coin, its spin could be up and down at once. It carries dual existence, overlapping states that only separate when we observe. We call this superposition. The moment of observation, the measurement forces it to decide. But what counts as a measurement? Is it a human observer with eyes and awareness? Or is a photodiode enough, a cold sensor recording without consciousness? The universe doesn't say. In some interpretations, the measuring device and the observer are part of one grand entangled system, like nested Russian dolls of observation. Each level collapses another, but none can tell where the process truly begins. This uncertainty ripples into everything we think we know. If a particle's position isn't fixed until observed, then between measurements, what is it doing? Whereas quantum mechanics tells us only the probability of finding it here or there. Reality becomes a cloud of likelihoods, not certainties. And yet, paradoxically, these blurred predictions match experiment with uncanny precision. Every transistor, every laser, every magnetic resonance image relies on equations that no one fully understands. Quantum theory works perfectly, even if its meaning slips through our fingers. Consider this: the world around you. The glow of your phone screen, the rhythm of your heartbeat measured by a quantum sensor, is built upon a theory that claims nothing truly exists until it is measured. It's as if every heartbeat, every photon of light waits for recognition before becoming real. Einstein called this incompleteness unbearable. Do you really believe, he asked, that the moon does not exist when no one looks at it? Niels Bohr smiled and said nothing. For Bohr, physics wasn't about what is, but what can be known. And here we are, caught between two truths. The universe unfolds according to mathematics that deny determinism, yet give rise to order. The act of looking shapes what is seen. Certainty, that ancient comfort of science, dissolves in the glow of a single photon. There was a time when physics felt like victory. Each new equation unlocked a secret of nature, each discovery promised clarity. But then came quantum mechanics, and the triumph turned uneasy. The deeper scientists understood, the more the ground beneath them trembled. Imagine standing in a lecture hall in the 1920s. Chalk dust hangs in the air like cosmic dust. Niels Bohr sketches the atom on the blackboard, its orbits shrinking into abstraction. Across the room, Albert Einstein folds his arms, his brow furrowed. The equations are flawless, they predict every result. And yet to Einstein they whisper something unbearable: randomness. He mutters his protest like a prayer: God does not play dice. But the dice kept rolling. Erwin Schrödinger, who wrote the wave equation itself, soon confessed regret. "I wish I had never met that damned cat," he said years later. His famous thought experiment, half alive, half dead, was meant as a critique, not a celebration. He had built the cathedral of uncertainty and found himself trapped inside. Richard Feynman, decades later, would laugh nervously about it. Nobody understands quantum mechanics, he admitted, and behind the humour was awe tinged with fear. For these were not students confused by complexity. These were the architects themselves, shaken by the house they had built. You can feel their unease, can't you? Equations that worked too perfectly, like mirrors reflecting not reality, but imagination. When Heisenberg introduced his principal uncertainty as law, it wasn't poetry. It was despair disguised as mathematics. You cannot know both the position and momentum of a particle, not because of weak instruments, but because nature itself refuses to be fully known. Now imagine being that scientist. You look at the wave function pairs, an elegant symbol that describes 1,000 possibilities, and realize it's more real than the things it represents. The math lives in a realm where intuition collapses. The world, once mechanical and measurable, now behaves like an idea that thinks back. Einstein tried to anchor it with hidden variables, unseen factors that would restore order. Bohr refused. He said the act of observation completes reality, that physics is about what can be said, not what is. Between them lay a philosophical fault line that still cracks beneath our feet. Even now, the paradox remains a theory that predicts everything, yet explains nothing about why. Quantum mechanics does not tell us what's truly happening beneath the surface. It only gives the odds. It is a casino that never lies but never shows the dealer's hand. And so, the scientists did what humans always do when faced with the incomprehensible. They kept working, pretending calm. But deep down, they sensed the truth. The universe is not a clockwork built to be solved. It is a wave, restless, observing itself. The equations have not failed us. They have outgrown us. They speak a language the human mind can write but not understand. At the end of our last step, we left the scientists standing before equations they both revered and feared, symbols that seemed to work while defying reason. Yet buried inside those same equations was another revelation. One even stranger: they did not care about direction. Whether time moved forward or backward, the mathematics remained unchanged. So let's begin there on the edge between cause and effect. You and I are standing in a darkened theatre. The screen flickers to life. A drop of ink spreads through a glass of water, curling like smoke. Now the film reverses. The ink gathers itself again, spiraling back into a single droplet. It looks impossible, yet the physics, the pure equations of motion, allow both versions. Newton's laws, Maxwell's electromagnetism, even Schrödinger's equation, they all run cleanly backward. To mathematics, the arrow of time is invisible, but we feel time moving, don't we? We age, we remember, we burn fuel but never unburn it. A shattered cup doesn't leap back together, and the sun's warmth never flows from cold space back to its core. Somewhere between math and memory, time picks a side. The question is why, in the quantum realm, that choice becomes a riddle. The fundamental equation of quantum mechanics. The Schrödinger equation describes how the wave function evolves in time, yet nothing within it says which direction time must flow. The function can evolve toward the future or rewind toward the past, and both are equally valid. Reality, it seems, does not recognize the word before. Imagine standing before a quantum experiment, a single photon fired toward a mirror. The device is perfect, it reflects every time. Now play the event backward. The photon retraces its path, hits the source, and everything still satisfies the laws of physics. No contradiction, no penalty. The universe allows the script to be read in reverse, as if time itself were a palindrome. That is time symmetry. The equations hold, the probabilities remain, the energy conserved. But we humans live in a world of entropy, the measure of disorder that always increases. It is entropy that gives time its direction, a one-way flow from low order to high chaos. Yet quantum mechanics whispers a rebellion on the smallest scales. Entropy sometimes flinches. Particles tunnel backward through barriers. Photons appear to coordinate across moments, as if anticipating what comes next. So which is true? Does the universe truly run forward, or do we simply ride one current among many? You might imagine time as a frozen river, each moment a crystal layer stacked upon the next. Our consciousness moving slice by slice gives the illusion of flow. The past doesn't vanish. It remains embedded in space-time like pages already written, and the future perhaps is already there unread. For most of physics, this isn't a problem. Equations predict outcomes just fine. But when observation enters the story, when measurement collapses, the wave function, the direction of time, suddenly matters. The collapse seems to move only forward, never backward. We cannot unobserve a photon once it has been seen. Yet the mathematics beneath it, the reversible core, keeps whispering that we should be able to. Einstein once compared time to a stubborn illusion. For us believing physicists, he wrote, the distinction between past, present and future is only a persistent illusion. And perhaps he was right. Time does not flow like a river. It is the riverbed itself, silent and unmoving, while consciousness drifts upon it. Still we cling to the arrow. It gives us meaning, beginnings, middles, endings. Without it, everything would happen at once, and causality, our faith in cause and effect, would crumble. Yet in the next experiments we will see this arrow bend, even break. We've just seen how the equations of nature seem indifferent to direction, how time itself, when written in mathematics, flows both ways without conflict. But now comes the moment where that abstraction becomes something almost unbearable. Because in one quiet experiment, physicists discovered that what we choose to do now can alter what reality seemed to have already done then. Imagine standing in a dark lab, your hand resting on a console that fires single photons, tiny quanta of light, one at a time toward a barrier with two slits. The setup is simple, elegant, ancient in spirit. It's a modern descendant of Thomas Young's double-slit experiment, first performed in 1801, which revealed that light behaves like a wave, not just a stream of particles. In this version, however, each photon is also recorded its which path information, stored or erased after the fact. This is the delayed choice quantum eraser, an idea first proposed by John Archibald Wheeler, the same physicist who coined the term black hole. Wheeler asked a heretical question. What if the decision of how we measure a photon, whether to observe its path or not, is made only after it has already hit the screen? To put it plainly, we decide in the present how the photon behaved in the past. Let's walk through it together. A photon leaves the source. It travels toward a pair of slits, each leading to a detector. If we record which slit the photon went through, we destroy the interference pattern, the hallmark of wave behavior. The photon acts as a particle, choosing one slit or the other. But if we erase that information, if we make it impossible to know which path it took, the interference pattern reappears as though each photon passed through both slits simultaneously. Here's the twist. The choice to record or erase that path can be made after the photon has already been detected on the screen. It's as if the photon waits for us to decide what story we want it to tell. Now close your eyes for a moment. Picture that photon leaving the emitter, just one grain of light crossing a distance of perhaps a few meters a journey, lasting less than a billionth of a second. In that tiny instant, you might think the event is complete sealed in the past, yet the outcome is not settled until you in the present decide whether to preserve or delete its path information. If you choose to keep the record, the photon seems to have behaved like a particle all along. If you choose to erase it, the photon seems to have behaved like a wave, but you made the choice after it arrived. It's as though the past has been rewritten not metaphorically, but literally within the mathematical description of the system. How can that be? Did the photon somehow know what you were going to do? Did the act of measurement send information backward through time? Wheeler's answer was quieter and deeper. He suggested that the photon's behavior is not fixed until the entire experimental setup, including your decision, is complete. In his words, no phenomenon is a phenomenon until it is an observed phenomenon. This implies that reality at its core is not built from independent things happening in sequence. It is woven from relationships, webs of interaction that stretch across time as easily as across space. Think of the experiment as a story told by the universe itself, but written all at once. The photon's journey, your decision. The detector's clicks, they all exist as a single indivisible event. The sense of before and after belongs to us, not to the cosmos. Now let's translate that into something tangible. Imagine you're filming a slow-motion video of a drop of water falling into a pond. You can play the footage forward or backward, it's beautiful either way. But in the quantum world, it's as if your decision to play it backward changes how the drop originally fell. The film isn't static. It rewrites itself depending on how you choose to watch it. That's the vertigo of retrocausality, the idea that the future can reach back and reshape the past. It's not time travel, not in the science fiction sense. It's deeper a suggestion that time itself might not be a sequence of events, but a network of relationships that can only be understood as a whole. The delayed choice quantum eraser demonstrates this eerily. In one implementation, photons are entangled pairs born together, their properties linked no matter how far they travel. One photon goes toward a detector screen forming a pattern. The other photon, its twin, is sent through a maze of mirrors and beam splitters. There an experimenter can choose, after the first photon has already hit the screen, whether to keep or erase the which path data. And yet when the results are compared later, a strange harmony appears. Only those photons whose partners had their path information erased show interference. The rest do not. The effect seems to ripple backward through time-sinking events that no classical explanation can connect. But physicists warn no signal travels to the past. No causality is truly broken. What happens is subtler. The universe does not store a definite history until we ask for one. Between question and answer lies a shimmer of ambiguity. Reality in this view is participatory. It becomes what it is through the act of engagement. Wheeler once gave this thought a name, the participatory universe. He imagined every act of observation as a thread that helps weave the fabric of reality itself. Even the light from distant galaxies traveling for billions of years might not have decided whether it behaved as a wave or a particle until it reached our telescopes. The cosmos, he said, is a kind of self-excited circuit, a loop in which the universe observes itself through us. Think of that for a moment. You look at a star that emitted its light when dinosaurs walked the Earth. That light has crossed interstellar space for 100 million years, a distance of roughly 1 trillion kilometers. and yet in a quantum sense it has waited for you. When you open your eyes, when your telescope detects it, its long, uncertain journey resolves into a single outcome. The past solidifies around your gaze. If this makes you feel dizzy, you're not alone. The delayed choice quantum eraser is less an experiment than a mirror held up to existence. It tells us that time may not flow from cause to effect, but may form a seamless whole where observation completes the pattern. The present touches the past, and the future shapes the story of what was. If the delayed choice experiment hinted that the present could reach into the past, retrocausality dares to say it outright. It is the whisper that maybe events are not chained in one direction. Perhaps the future is not a destination we travel toward, but a partner already leaning back to meet us. Picture again that photon from the previous experiment, its journey stretched between emitter and detector. In the standard view, it begins in the past and moves forward, guided by the Schrödinger equation, smooth deterministic indifferent to time's arrow. But what if there's another wave moving the other way? One from the future converging backward through time, meeting its twin from the past in the middle. This is the essence of the two-state vector formalism proposed by Yakira Haronoff and his colleagues. In their model, every quantum event is described not by one wave function, but by one evolving forward from the past and another evolving backward from the future. The outcome we observe the now of the experiment is the handshake between them. It's as if reality is a negotiation between what has been and what will be. Let's make that tangible. Imagine standing at the midpoint of a bridge. Behind you stretches everything that has happened. Ahead lies everything that could happen. Aharonoff's idea says you exist not only because of the past that built you, but also because of the future that requires you. The photon doesn't simply travel forward, it also feels where it must end up, and the two influences meet halfway, agreeing on what truly occurs. Retrocausality then doesn't send messages backward in time. It reshapes how we think of cause itself. The universe may not be a line of dominoes toppling one by one, but a complete mosaic in which every tile finds its position only when the pattern is seen as a whole. The past doesn't create the future. Both co-author the present. Some physicists call this the block universe, a vast four-dimensional structure where every moment, past, present, future exists simultaneously, like frames in a film reel. Consciousness gives us the illusion of motion scanning through each frame sequentially. But to the cosmos, the story is already complete. Every photon, every heartbeat, every choice you make is another coordinate in that timeless architecture. Still, something about this symmetry feels unsettling. If the future can influence the past, where does free will stand? Are we just reading a script already written? Or are we through observation, through awareness, co-writing it in real time, adding ink to an eternal manuscript? Einstein once said, "The distinction between past, present, and future is only a stubbornly persistent illusion." Aharonoff went further. The future is as real as the past. So perhaps the act of looking forward is not a prediction, but participation. Perhaps the light of tomorrow doesn't wait for us to reach it. It has already been shining this way all along. When we last stood together, we left the universe suspended between two arrows of time, one pointing forward, one leaning back. The future illuminating the past folding quietly into the present. But even that vision assumed there was still one reality holding it all. Now we must ask a deeper question. What if reality itself fractures the moment we look at it? Imagine a quiet laboratory sealed from the world. Inside stands a scientist, Wigner's friend. She prepares a quantum system, perhaps a single electron trapped in a magnetic field. Its spin can be up or down, but before she measures it, it exists in both states at once, a delicate superposition, pecs shimmering between possibilities. She performs the measurement. Her instrument clicks. For her, the outcome is clear: the electron is spin up. The world in that instant collapses into one version. Outside the lab stands Eugene Wigner himself. To him, his friend, her mind, her machine, the entire room is still part of a larger quantum system. Until Wigner opens the door and asks what she saw, the entire laboratory exists in superposition, a blend of friend saw up and friend saw down. Inside, she feels certainty. Outside, he calculates uncertainty. Two observers, two realities. This is the paradox known as Wigner's friend, first proposed in 1961 and revived by modern experiments in 2019. And here is the unsettling truth: both perspectives are equally valid within quantum theory. Now step with me closer. Imagine standing between them, one on each side of the door. Inside, the air hums with instruments. Outside, equations fill the air like murmured prayers. The same event, the same particle, the same universe, and yet two incompatible truths exist at once. You and I are used to thinking that the world is shared, that facts are communal. But here, fact itself becomes a relational something that depends on who, and perhaps what, is doing the observing. In 2019, a team at Heriot-Watt University performed an optical version of this thought experiment using entangled photons. Their results mirrored Wigner's nightmare. Two observers can record different realities that cannot both be reconciled. There is no single fact of the matter, and here something deep begins to tremble. If reality can split between two observers, if measurement is personal, not universal, then objectivity itself may be a convenient illusion. Think of it this way. Imagine two musicians each wearing headphones listening to the same symphony through separate channels. One hears a violin, the other a cello. They tap to the rhythm, confident they share the same melody. But when they remove their headphones, the music collapses into a single recording, and each swears the other must be wrong. Quantum mechanics suggests that both were right. Until the world compares notes, both symphonies coexist. This idea doesn't just challenge logic, it rewrites it. It suggests that the universe may hold countless coexisting versions of itself, branching with every act of measurement. The many worlds interpretation takes this literally. Every observation splits reality into new branches, each as real as the next. In one branch, the electron is spin up, in another spin down. You, the observer, also divide, following each path into its corresponding world. To picture it, imagine a forest at night. Each time you shine your flashlight, the light forks thousands of beams spreading through mist. Every choice you make is one of those beams illuminating one path, while countless others fade from view. Yet they do not vanish. They continue unseen, complete. And here comes the human question. If each observer lives in their own branch, where do we meet? What does it mean to share a reality at all? Perhaps communication. The exchange of observation is the act that realigns realities, forcing them into temporary agreement. When Wigner opens the door and speaks to his friend, her world and his synchronize. Information flows, superpositions collapse, consensus forms. The illusion of a single world returns, at least for a moment, but under that surface the fractures remain. Einstein once said reality is merely an illusion, albeit a very persistent one. Wigner's paradox shows how fragile that persistence truly is. The solidity of the world may depend on a network of observers continually comparing experiences, stitching together a shared illusion from incompatible truths. Let's take a breath here. You and I, observers ourselves, are part of that network. Each time you look, measure, decide, the universe reshapes itself around your perception. Every sight, every thought is another small collapse of possibility into actuality. You are both the witness and the participant, both the friend and Wigner outside the door. The paradox is not a trick of mathematics. It's a mirror held up to consciousness. So as we leave the sealed laboratory, imagine glancing back through the small window in the door. Inside, instruments still blink. Outside, equations still glow. Between them, something invisible stretches a filament of awareness, linking two incompatible truths into one trembling tapestry. Reality, it seems, is not singular. It is plural, shimmering, deeply personal. And if it can differ between two minds in one room, then perhaps across the cosmos, countless versions of truth ripple through the same vast silence. If two people can disagree about the same event and both be right, what happens when two particles share a thought across the stars? Perhaps communication itself no longer needs a voice. We step into another lab now, lightless, quiet, except for the soft click of detectors. On the table lies a crystal that emits twin photons, two specks of light born together, entangled at the moment of creation. They speed away in opposite directions, perhaps a few meters apart here, or billions of kilometers apart out there between stars. Yet somehow whatever happens to one is instantly mirrored in the other. You measure your photon, it spins clockwise. I measure mine, it spins counterclockwise. If we both rotate our detectors, turning them at random angles, the correlation remains stronger than any classical logic can allow. It is as if both photons consult the same hidden script, even though no signal traveling at the speed of light, about 300,000 kilometers per second, could pass between them in time. Einstein called this Spukhaft, Fernwirkung, spooky action at a distance. Today we call it entanglement, to understand the impossible physicists invented games. One is known as the GHZ game, named after Greenberger, Horn and Zeilinger, another the Magic Square. In these experiments, 2 or more players, each isolated, forbidden to communicate, use entangled particles to coordinate answers to puzzles that by ordinary probability they should almost always lose. Yet quantum players win every time. This eerie advantage is called quantum pseudo-telepathy because no information actually travels between them, and yet telepathy because the results feel like shared intuition. Imagine 2 musicians on opposite sides of the galaxy, each striking notes on a piano. No sound can bridge the gap, no message can cross the light years between them, and still every chord is in perfect harmony, every beat in time. How can that be? The mathematics says the correlation is not caused after the fact it was never separate to begin with. Entangled systems are described by a single wave function, picks one equation that spans both particles. To speak of one or the other alone is meaningless. Together they are one organism stretched across space. The universe in this view is not a collection of independent objects, but a vast interwoven field of relationships. What we call distance is just geometry within that field. You might picture the cosmos as a great fabric like the surface of a drum. Touch it in one place, and the vibration is felt everywhere at once. The drum does not send a message, it simply resonates as a whole. Still, the implications disturb us. If correlation exists without communication, what does that say about reality itself? Maybe separation is an illusion born of scale. From far away, a wave looks like many ripples. Up close, you see it's one continuous motion. The photons, the detectors, even you and I, perhaps all parts of one extended pattern, not isolated minds, but nodes of coherence. It is here that quantum mechanics brushes against philosophy. The language of particles begins to sound like the language of perception. When you think of someone across the world and they call at that exact moment, we dismiss it as coincidence. Yet the physics of entanglement reminds us correlation without communication is not impossible, it's fundamental. In 2015, experiments in Delft, Vienna and Boulder closed every loophole. Entanglement was real. Bell's inequalities were violated beyond doubt. The world does not behave like a local machine. It behaves like a single organism that knows itself. So the silence between the photons is not emptiness, it's structure. The gap between us, between galaxies, between moments, might not be a void, but a bridge invisible to our eyes. And if 2 particles can dance in perfect synchrony without a signal, then perhaps minds emergent from the same quantum fabric can resonate too. If 2 particles can share a thought across galaxies, we might imagine we've reached the limit of strangeness. But the quantum world always has another step beyond the edge. The next paradox is not about distance, it's about identity itself. What if an object could be in one place while its properties wandered somewhere else? Let's return to the lab dimly lit. Now the hum of machinery softened like a heartbeat. Here physicists send neutrons through a device designed to separate their paths. One route bends left, the other right. As each neutron travels, it carries a spin, a kind of tiny magnetic compass, pointing either up or down. Normally we assume the neutron and its spin go together like a dancer and her shadow. But in 2014, researchers at the Institut Loewe-Langevin in France discovered something that defied that assumption. Using a technique called weak measurement, they found that the neutron's body took one path, while its spin appeared to take another. The neutron went one way, its property, its essence went another. This became known as the quantum Cheshire cat, named after the grinning feline from Alice's Adventures in Wonderland, whose body fades until only its smile remains. Imagine standing before that device watching 2 faint streams of data trace across separate screens. One signal says the particle was here, the other says its spin was over there. Both measurements are real, consistent and verifiable, and yet they should belong to the same thing. It's as though the smile has slipped from the face, drifting through the air untethered but still very much alive. Weak measurements are like soft whispers. They probe a system gently enough not to collapse its quantum state. Through them, scientists can infer where properties prefer to be without destroying the delicate superposition that defines them. In the neutron experiment, that whisper revealed an unsettling truth. The attributes of an object charge spin polarization might not be permanently attached. They can separate, float, and recombine. So what then is the object? If a particle can leave its properties behind, is the particle the substance, or merely the meeting point of attributes? The quantum Cheshire cat forces us to see reality not as a collection of solid things, but as a network of relationships like a melody that exists only when notes are played together. You and I can feel this intuitively. Consider how memory and emotion work in us. Sometimes a place remains vivid long after the person has gone, a laugh echoing in an empty room, a familiar scent lingering in the air. The memory is there detached like a property that refused to vanish. In the same way, the neutron's spin seems to remember where the particle once was. Space, it turns out, may not bind identity the way we think. In the mathematical language of quantum theory, this phenomenon arises because the particle's wave function, P, the pattern of probabilities, can spread across regions. Different parts of P's can encode different observables, so position and spin need not overlap. Reality, once again, is not about things, but distributions of possibility. It's tempting to ask, could this happen on larger scales? Could attributes like consciousness or intention ever drift free from the matter that hosts them? No experiment says yes. But the idea feels uncomfortably close to something ancient, the human intuition that essence and form are not the same, that what we are might extend beyond what we see. And so the Cheshire Cat grins at us from the border between physics and philosophy. Its body is gone, its smile remains. Its laughter echoes through equations that describe a world where matter and meaning no longer coincide. If the Wigner's friend experiment questioned who is right, and entanglement questioned what is connected, then this paradox asks something simpler and deeper. When we say something exists, what do we actually mean? Is existence the thing itself, or the trace it leaves behind? If the Cheshire Cat taught us that a smile can exist without its face, what about the observer, the one who sees the smile? What if awareness itself could survive the collapse of every possible world? This is the shadow doorway of the quantum suicide paradox, one of the most haunting interpretations of quantum theory. Let's begin slowly. Imagine you're sitting in a laboratory, once again surrounded by quiet instruments and faint blue light. Before you is a device, a perfectly calibrated quantum trigger, connected to what can only be described as a gun. Each time you press the button, the device measures the spin of a single particle, an electron or an atom, its orientation either up or down. If it's spin up, nothing happens. If it's spin down, the gun fires. The rule is 50-50, half the time death, half the time life. Now take a breath, because here comes the thought experiment. You press the button. The gun does not fire. You press again. Again silence, and again and again. No matter how many times you try, you always find yourself alive. But how? To the outside world, this seems absurd. Observers watching from beyond your sealed lab would say that half the branches of reality end with your death. But you, the first-person observer, never experienced those branches. In the Many Worlds interpretation, Hugh Everett, 1957, the universe splits every time a measurement occurs. One version of you dies, another lives. Yet your conscious experience only continues in the branch where you survive. From your own perspective, you are immortal. This is quantum suicide, the personal mirror image of Schrödinger's cat. In the cat's box, both life and death coexist until observation collapses the state. But from inside the box, the cat always finds itself alive. Now let's bring this closer. Imagine you sitting there, heart-steady eyes fixed on the device. Around you, the laboratory feels unchanged, though countless invisible worlds have just branched away, each one holding another version of you, who did not make it past the last click. From within your own awareness, you cannot sense those other universes fading. To you, the story continues unbroken, an endless corridor of survival. In one branch, the gun fired, but the you is gone. In another, the gun jammed and the experiment resets. Your consciousness walks the only path it can, the one that endures. This is not mysticism, it's logic carried to its edge. Quantum mechanics tells us that all possible outcomes exist, but consciousness can only inhabit one. The unsettling consequence, in at least one branch, you never die. Let's pause here because it sounds like a promise, but it's really a paradox. Physicists like Max Tegmark have debated it for decades, pointing out that from a third-person viewpoint, all branches are equally real, yet no branch is more privileged than another. From your viewpoint, however, subjective continuity never ends. Death is simply the absence of awareness, and you cannot experience that absence. So in theory, you always find yourself on the path that survives. But this immortality is not the romantic kind. It is cold, mechanical, statistical. With every survival, the world around you changes slightly different noise, different dust motes, different histories where others did not continue with you. You drift through the thinning probability of existence further and further into branches where your survival grows less likely, until even that improbability becomes your reality. Picture yourself as a traveller in a forest of infinite trees. Each choice, each quantum event splits another path. Some trails end abruptly, others twist deeper into unknown territory. You cannot step into the paths where you no longer exist. Your consciousness follows only those that remain lit. And so for you, the forest never ends. This is the unsettling beauty of Everett's multiverse. Every possibility is realized, but awareness can only ride one stream. To the universe, there are countless yous. To you, there is only the one who survives. It is an immortality not of body, but of perspective. Now imagine observing this from outside. To the external physicist like Wigner outside his friend's lab, there is no miracle, only branching equations. But from the inside, you're the miracle, the observer who can never watch themselves cease to be. What does that say about consciousness? Is it a property of matter, like charge or spin? Or is it something stranger? Something that clings to survival itself, like light refusing to go dark? Maybe awareness is the universe's way of ensuring continuity, a single thread that always finds its way through the branching labyrinth of possibilities. You can feel the paradox pressing close now. If every observation collapses one world and preserves another, then every heartbeat is also a kind of measurement, a quantum declaration I'm still here. The mind, by existing, ensures its own persistence. But immortality through branching comes with a haunting cost: isolation. Each step forward narrows the world to one line, one surviving version of you, while infinite others fade into silence. So we return to the same quiet question. If you can never experience your own ending, does death truly exist for the observer? Or is it only another event in a branch you will never see? You might close your eyes now, and in every possible world, another version of you does the same. Some will wake, some will not. But the only one you can ever know is the one who does. If consciousness can linger along the surviving branch, then perhaps the universe itself holds a similar vow that nothing once known can ever truly disappear. Nowhere does that vow feel more fragile, more violated than at the heart of a black hole. Imagine one hanging in the dark, far beyond the Milky Way's spiral arms, a void so dense that even light cannot escape. Around it, stars swirl like fireflies circling a drain. You and I stand at a safe distance, watching matter fall inward. Gas dust-even planets spiral down, stretching into ribbons of plasma glowing hotter than any forge. From our perspective, as the debris nears the event horizon, time itself slows. Every photon escaping toward us climbs out more faintly, redder, weaker. To us, the falling matter seems to freeze in place, a silent image hovering at the edge of forever. But from its own frame, that matter crosses the boundary and vanishes, never to return. And so a question arises. What happens to the information describing that matter, its atoms, spins, quantum states? If it is gone, the laws of physics are broken. Stephen Hawking faced this paradox in the 1970s. According to his calculations, black holes are not perfectly black. They radiate faint heat. Hawking radiation, a ghostly glow formed by quantum fluctuations near the event horizon. Virtual pairs of particles born from empty space can split, one falls and one escapes. The escaping one carries energy away and the black hole slowly evaporates. But here lies the problem. The escaping radiation is thermal random. It seems to carry no information about what fell in. When the black hole finally evaporates, all the encoded detail of the universe's past would be gone forever. Yet quantum mechanics forbids that. In the quantum world, information is sacred. It can change form, hide, or scatter, but it cannot be destroyed. The conflict between general relativity and quantum mechanics became one of the deepest wounds in physics, the black hole information paradox. Let's picture it more simply. Imagine a diary thrown into the sun. The pages burn, but the smoke ash and heat still contain every detail in microscopic form, scattered but not lost. In black holes, the question is crueler. Does the universe still remember what went in, or has that record been erased from existence? Some physicists proposed that the information remains imprinted on the surface of the event horizon itself, encoded like data on a cosmic hard drive. This is the holographic principle suggested by Gerard de Hooft and Leonard Susskind. It says that everything happening inside a region of space can be described by information stored on its boundary. In other words, the three-dimensional universe may be a hologram projected from a two-dimensional surface. Others went further, proposing the firewall hypothesis that the horizon might burn violently, destroying anything that crosses it to preserve information consistency. But if so, then the smooth space-time predicted by Einstein would shatter. Even the calmest black hole would hide an inferno beneath its dark surface. And still, somewhere between gravity and quantum logic, another idea shimmers. Perhaps the information never truly crosses the boundary. Perhaps it's encoded in subtle correlations between the radiation that escapes and the hole that remains. In that case, the black hole doesn't destroy memory. It scrambles it, turning it into a perfect encryption. To an outside observer, it looks lost. To the universe itself, it is preserved in patterns too deep for us to read. When you think about it, that sounds almost familiar. Our own minds do something similar. Memories vanish from reach, yet traces remain reorganized, hidden, but never entirely gone. So maybe black holes are not cosmic destroyers at all, but cosmic archivists. Every photon, every life, every whisper of matter that ever fell in, still there, written in light, too tangled for our eyes to decipher. If consciousness can persist through every quantum split and information can survive the fall into oblivion, then perhaps the universe itself has made a promise. Nothing truly ends, only transforms. We have followed the numbers to their edge across paradoxes of time through branching worlds, and now into the throat of a black hole. The equations still hold, still calculate, still predict. But something has shifted. The formulas describe how the universe behaves. They no longer tell us why. Stand with me in the dim glow of the lab where chalk dust hangs like cosmic dust in the air. On the blackboard, the symbols still gleam PSEHG. They are constants, the bones of reality. They have served faithfully, describing the curvature of space-time, the shimmer of probability, the dance between gravity and quantum fields. Yet even here, among elegant equations, there is an emptiness that mathematics cannot bridge. Einstein once confessed the most incomprehensible thing about the universe is that it is comprehensible. But even comprehension, it seems, has boundaries. We can write the equation for a collapsing star, for the temperature of Hawking radiation, for the entanglement entropy that guards information at the event horizon, and still not know what happens. Because to calculate is not to understand. Perhaps we expected too much of our symbols. They have given us predictions, technologies, and maps of the invisible. But the deeper we go, the more the universe begins to sound like a poem, written in a language only half known, precise in grammar, mysterious in meaning. You can feel it too, can't you? That faint sense that the cosmos knows something it refuses to translate. Maybe the equations are like footprints, the traces of an intelligence greater than our own. Or maybe they are reflections, our minds catching glimpses of themselves in the mirror of existence. Either way, when we reach the limit, the chalk stops and silence begins. It's the same silence you hear between stars, the same pause between breaths, the same stillness that lingers after every act of discovery. If consciousness mirrors the universe, and the universe preserves every fragment of memory, then maybe we and the cosmos are solving each other two halves of one unfinished equation. Perhaps that is why every great physicist ends not with certainty but with wonder. Bohr called it complementarity. Heisenberg called it the limits of knowledge. Hawking near the end simply said, "We're just an advanced breed of monkeys on a minor planet, but we can understand the universe. That makes us something very special." So here we stand, formulas glowing behind us, silence before us. We've reached the threshold where knowledge becomes awe, and from that quiet one, truth still hums like background radiation. The universe is not obliged to make sense. It only invites us to keep listening. If every equation ends in silence, perhaps what we're missing isn't in the math at all, but in the act of seeing. The next mystery waits not in the stars, but in the observer's own gaze. We have followed the paradoxes of time and space, watched particles split from their properties, and now we arrive at the quietest and most fragile question of all. When does possibility become reality? In quantum physics, everything begins with what we call the wave function. Its symbol is the Greek letter psi. Psi describes every possible state of a particle, not where it is, but where it could be. It spreads like a fog of probabilities covering every direction, every point in space. Only when we observe it, when a measurement takes place, does that fog appear to collapse into one definite outcome. We call this moment the collapse of the wave function. But here lies the riddle. The equation for psi governed by the Schrödinger equation never tells us when or how this collapse should occur. There is no built-in timer, no signal, no mathematical clause that says now. It simply evolves smoothly indefinitely until something or someone looks. Imagine standing in a vast dark dome filled with countless invisible stars. Everywhere could be a spark or nothing at all. Then you lift a lantern, its light like a measurement, and suddenly one single star glows back at you. All the others remain hidden, unchosen. That's how the quantum world behaves. Before you look, every outcome exists as a ghost of probability. When you measure, one possibility crystallizes into the real and the rest fade into silence. This is known as the measurement problem, and it has haunted physicists for a century. What exactly counts as a measurement? Does it require a conscious mind? Is a machine enough? Or does the universe somehow measure itself through constant interactions between particles? Niels Bohr believed that reality only becomes definite when observed. Albert Einstein refused to accept that. He once asked, "Do you really believe the moon isn't there when no one looks at it?" And Bohr, smiling quietly, replied, "Can you prove that it is?" That single exchange became one of the deepest divides in modern physics. Out of it came dozens of interpretations, all consistent with experiment yet wildly different in meaning. Some physicists say that psi isn't real at all, it's only a tool for predicting probabilities. Others, like the proponents of the many worlds interpretation, argue that the wave never collapses, instead reality branches. Each possible outcome becomes its own world, and you live only in the branch that matches your observation. Still others propose that the collapse is physical, maybe tied to undiscovered variables, or perhaps to conscious awareness itself. Each theory feels complete, and yet none truly satisfies the silence at the center. Close your eyes for a moment. Picture one electron, unimaginably small yet fundamental. Its wave function, ESI, extends wider than a mountain range, yet the instant you measure it, it appears at a single point. How does the spread of possibility collapse into that tiny certainty? Did your act of measurement cause it? Or did it simply reveal what was already there? The wave function gives us no hint. It never says when to collapse, because maybe it never truly collapses at all. Perhaps reality is not a sequence of events, but an ongoing conversation between what might be and what is seen. Perhaps psi never chooses, you do. And maybe that silence, that absence of instruction, isn't a flaw in the math, but a message from the universe itself that the act of seeing is inseparable from the thing seen, and that we too are part of that shimmering field of possibilities, a wave aware of its own collapse. If the wave function at psi never says when to collapse, then maybe the answer is not inside the equation, but somewhere in the space between the particle and the one who looks. You and I stand now on that invisible border. On one side lies the world of matter atoms, electrons, photons, each following the calm mathematics of quantum theory. On the other side stands the observer, our eyes, our instruments, our awareness, the thing that knows. Every time we measure something crosses this border. A particle that was spread like mist becomes a single dot. An uncertainty becomes a fact. It is as though the act of seeing translates probability into reality. But who or what performs that translation? John von Neumann, the mathematician who built the foundations of quantum logic, once drew a chain from the detector to the measuring device, to the nerves, to the brain, to the observer. He asked, at which link does the wave function collapse? If the chain has no end, then the world would stay uncertain forever. But if it ends with consciousness, then the mind itself might play a physical role in shaping the outcome. Eugene Wigner, a Nobel laureate and one of the pioneers of the field, took this seriously. He proposed that the collapse happens only when the result becomes part of conscious experience. In his words, it is the consciousness of the observer that brings the phenomenon into being. It's a daring thought that awareness is not a bystander but a participant, that the universe becomes real only when it is known. Let's make this tangible. Imagine a single photon, the smallest particle of light traveling through an interferometer. It has two possible paths, left or right. Until you look, it behaves as though it takes both. When you finally detect it, the pattern changes. The photon decides, but perhaps that decision was not the particles alone. Perhaps it was the interaction, the handshake between photon and observer that crystallized the event. The universe then might not exist as a set of objects, but as a web of relationships, each one woven by an act of awareness. It's tempting to imagine that your consciousness is a lens focusing the diffuse haze of quantum possibility into the clarity of experience. When you look at the world, you do not merely record it, you participate in its formation. And maybe the same is true for the universe itself. Perhaps it observes through us, each of us, a cell in its vast cosmic retina, each perception, another flicker of existence coming into focus. If that is true, then the line between matter and mind is not a boundary at all, but a zone of creation, a living interface where energy becomes experience. And perhaps just as light needs both wave and particle to be complete, reality needs both the universe and the observer to exist at all. For more than a century, quantum mechanics has answered the question of how matter behaves, how probabilities evolve through the wave function as it follows the Schrödinger equation, how measurement transforms uncertainty into the certainty of a result. But physics at its deepest level eventually meets something it cannot quantify: the why. Why should the universe obey equations so precise that the energy of a hydrogen atom can be predicted to 14 decimal places? Why should consciousness which arose from matter now appear capable of shaping that same matter through observation? And why should information, not mass, not charge, not force, seem to be the most fundamental quantity of all? These are not metaphors, they are open questions in modern physics. When we speak of information, we mean the actual bits that define the possible states of a system, the quanta of difference. Entropy measures this. It is written as entropy S equals K times the natural logarithm of W. Here represents entropy K as Boltzmann's constant, approximately 1.38 times 10 to the minus 23 joules per Kelvin, and W is the number of microstates, the number of microscopic arrangements a system can have while appearing the same from the outside. Every interaction, every photon absorbed or released changes W and therefore changes S. Reality, it seems, is not made of substance but of transitions of choices recorded as information. In each quantum event, a possibility becomes a fact, and that fact is stored as data within the fabric of the universe. Energy and matter are only expressions of that deeper informational code. This is the foundation of what physicists now call quantum information theory, a framework in which the universe itself behaves like a processor, conserving information even when energy dissipates. John Archibald Wheeler, who first coined the term black hole, proposed something extraordinary: that the universe is participatory. He wrote, "The universe does not exist out there independent of us. We are part of the machinery that brings it into being." His phrase, "it from bit," captured this radical idea that every particle or event derives its existence from a bit, from an act of measurement, an exchange of information between observer and observed. Today, this idea resonates far beyond philosophy. Experiments in quantum computing and decoherence show that information never disappears. It can only be transformed or hidden, a principle supported by the no-hiding theorem and by studies of black hole entropy, where information seems to be encoded on the event horizon rather than lost inside. In this view, the universe is not a vast collection of objects, but a self-maintaining conversation made of data. So the question how becomes insufficient. The equations describe how the world unfolds, but not why this dialogue between matter and awareness exists at all. Perhaps why cannot be found within the system because we are part of it. The observer cannot step outside the universe to watch it form. We are woven into the very act of witnessing. When we measure, the universe measures itself. When we ask, the universe learns the question. The shift from how to why is not a failure of science. It is the boundary where knowledge becomes self-reflection, where physics begins to curve back upon consciousness. Maybe this is the real nature of the cosmos, a network of interactions that knows it is interacting, a field of information aware of its own persistence. The mystery then is not that we can understand the universe, but that the universe produces beings who can ask why. Perhaps that question, not the answer, is what keeps the wave of reality unfolding at all. And if every why becomes a mirror, then paradox is not confusion, it is reflection, the universe observing itself to remember that it exists. Everywhere we look, there are patterns, and beside them paradoxes. They are not errors in calculation or gaps in logic, they are coordinates. Each paradox is a marker drawn on the boundary of understanding, a signal from the universe, whispering you have reached the edge of what you know. The measurement problem told us that observation itself defines what becomes real. The retrocausal hypothesis suggested that the arrow of time may not be one way, that events in the future can influence what we see in the past. Wiggins' friend paradox showed us that two observers seeing the same experiment may inhabit two equally valid realities. The quantum Cheshire cat separated a neutron from its spin, showing that attributes can wander without their owner. The quantum suicide thought experiment placed consciousness inside the many worlds interpretation framework and asked if awareness ever truly ends. And the black hole information paradox forced Einstein's geometry and quantum law to confront each other over whether information can be lost. Each of these anomalies is a dot on a single celestial chart: observation, time, identity, existence, memory. When connected, they form a shape, the outline of an unfinished understanding. Physicists sometimes call this region the domain of inconsistency, where equations still work but their meanings no longer align. It is the twilight between theories relativity perfect within the cosmic scale, quantum mechanics flawless at the atomic one, yet each refusing to speak the other's language. Notably, the Koch-and-Specker theorem reveals that hidden variable theories cannot embed context-independent values in quantum observables without contradiction. Meanwhile, the no-hiding theorem in quantum information theory asserts that lost quantum information must reside elsewhere in the system, not vanish entirely. These theorems show that the paradoxes are not just curiosities but deep signposts. They highlight structural limitations of our mathematics and our conceptions of reality. At such boundaries, paradox is not failure, it is invitation. The contradictions are not doors closing but cracks where new light enters. Relativity was born from the paradoxes of motion and light. Quantum theory rose from the paradoxes of measurement and uncertainty. The next revolution will rise from the paradoxes we face today, those that link information, consciousness, and space-time itself. Let's visualize this together. Imagine standing beneath a sky of paradoxes, each one a star of contradiction. The more we study them, the more constellations we begin to see: time folding into itself, matter woven with awareness, gravity whispering the language of information. You and I trace those connections like cartographers of the unknown. The lines form patterns, not chaos but geometry, not confusion but design. Science, after all, does not advance by certainty. It advances by curiosity, by daring to question the contradictions it cannot yet resolve. We orbit paradoxes the way planets orbit stars, drawn by their gravity, illuminated by their impossibility. Perhaps this is the real structure of knowledge, a universe that defines itself through tension, a cosmos whose deepest truths appear first as contradictions. Paradox is not the enemy of reason, it is its compass. Every question we cannot yet answer marks another direction to travel. If paradox is our compass, then what direction does it point to, toward unification or toward redefinition? Every physicist dreams of a theory of everything, a single framework that unites the cosmic and the quantum. Einstein spent the last decades of his life searching for it, trying to weave gravity and electromagnetism into one equation. Decades later, quantum field theory and general relativity still stand like two great continents, divided by an ocean of paradox. Both are flawless within their own domains. Relativity describes how space-time bends around mass and energy. It governs the geometry of galaxies and black holes. Quantum mechanics, anchored by Planck's constant h or h-bar when divided by 2π, explains the probabilistic dance of particles and waves. Each works perfectly. But when the two are combined, the mathematics collapses into infinities, as if the universe itself refuses to be described in a single breath. One path forward is unification. Physicists continue to search for a deeper law beneath both frameworks: string theory, loop quantum gravity, emergent space-time, each suggesting that what we call matter and geometry might be woven from the same informational threads. In these models, every vibration, every quantum of energy is part of one underlying fabric. The language of that fabric is not space or time, but information itself, perhaps measured by entropy. S equal to K log W, Boltzmann's relation between order and possibility. If the cosmos is informational at its core, then relativity and quantum mechanics are not separate laws, but two dialects of the same code. In recent decades, two ambitious frameworks have vied for this title. String theory proposes that all fundamental particles are tiny vibrating strings existing in 10 or perhaps 11 dimensions. The different modes of vibration generate every force and form. Loop quantum gravity, by contrast, quantizes space-time itself, building it from discrete loops or spin networks at the Planck scale around 10 to the power of minus 35 meters. String theory requires extra dimensions and supersymmetry. LQG remains four-dimensional and background-independent. They seem incompatible, yet both whisper of a deeper layer. Some researchers now suspect a subtle convergence that loop quantum gravity may describe the pre-geometric skeleton from which string theory's vibrating filaments arise. In that view, geometry and matter are two expressions of the same informational substrate. Reality becomes a fabric of data coded not in distance or duration, but in relationships, bits instead of fields, interactions instead of things. If such an informational cosmos exists, then unification is not only possible but inevitable. Energy, entropy, and information would be interchangeable currencies. Time itself would be a measure of computational change. The equation of everything would not be written in mass or length, but in logic, the syntax of existence. Yet there is another path: redefinition. Perhaps the goal is not to merge our theories, but to transform our idea of what a theory is. Maybe nature cannot be reduced to a single formula, because reality itself is relational, a network that only makes sense when viewed from within. In that case, the act of unification would not be mathematical but participatory, the recognition that every observer, every consciousness is part of the equation. This alternative sees the universe as a self-referential system, one that produces both law and observer simultaneously. Information does not merely flow through space, it constructs space. Observation is not a disturbance, but a completion of the process. The paradoxes we face, measurement, retrocausality, non-locality, may then be signatures of a participatory physics where the knower and the known form a single circuit. Stand here for a moment on that thin line between the measurable and the meaningful. Look upward, the stars obey gravity. Look downward, atoms obey quantum law. And between them stands the observer, the bridge where the two regimes meet. Perhaps that is what unification truly means, not compressing all equations into one, but realizing that the same awareness which asks the question is also part of the answer. If paradox is our compass, then the direction it gives is not linear but recursive. Science loops through its own assumptions. Each contradiction forces us to redefine what we mean by understanding. Maybe the next great revolution will not erase paradoxes at all, but accept them as structural as the curvature of knowledge itself. For every attempt at synthesis, there will be a counter-movement of reinterpretation. The two are not opposites, they are complementary phases of inquiry. Unification condenses, redefinition expands. Together they sustain the rhythm of discovery. The universe may never surrender one law that explains everything, but it keeps granting something far more mysterious a mind capable of asking why. That faculty, curiosity itself, could be the missing symmetry, the final variable that equations quietly assume but never express. Whether through unification or redefinition, the journey always turns inward toward the frontier where physical law and conscious awareness intersect. At that boundary, paradox no longer divides, it connects. Knowledge does not collapse, it converges. The equations remain, the observer remains, and both dissolve into a single continuity of understanding. There, science and philosophy are not two languages, but two frequencies of the same signal, one describing the structure of reality, the other describing the experience of perceiving it. And between them lies the silence that makes both possible. We have walked a long road through the unknown, from equations that predicted motion and matter, to questions that revealed the limits of knowing itself. Now we arrive at the quiet point where thought folds back on itself, where inquiry becomes reflection, and the circle closes. Every law we discovered was a mirror, every paradox a reflection of our own incompleteness. Relativity showed us that time and space are not fixed, but bend with the presence of mass, energy, and perspective. The paradoxes of consciousness reminded us that the act of observation is never separate from what is observed. In every experiment, the universe was never silent, it was responding. We looked into the atom and found probability. We looked into space-time and found curvature. We looked into awareness and found ourselves. The deeper science reached, the more it began to sound like a language of devotion, a chant of numbers that described not control but participation. The equations were never about dominance or certainty. They were invitations to witness, to listen, to become part of the unfolding symmetry. At this point, the boundary between scientist and mystic disappears. To observe is to pray in the dialect of physics, to calculate is to wonder with precision, and to ask why is to light another small lantern in the infinite dark. You can sense the pattern now, the breath beneath the data. Every discovery was not a destination but a heartbeat in an ongoing rhythm that began long before us. Perhaps the universe has always been whispering one message, repeating it through gravity, probability, and thought. You are part of this. Close your eyes. Feel how the silence hums with equations that no longer need to be solved. Feel how the air around you carries the residue of every question ever asked. This is not an ending, it is a return. The circle does not close, it breathes. Inquiry becomes memory, memory becomes wonder, and the observer always becomes the universe looking back. Across 4 centuries, science has refined one question. How does the universe behave? From Newton's laws of motion to Einstein's curvature of space-time, from Schrödinger's equation to the quantum field model, the machinery of description has been astonishingly precise. The wave function provides a full account of probability. Planck's constant h-bar defines the smallest unit of physical action. Boltzmann's equation S equals k times the logarithm of W connects entropy to the number of microstates. The constants remain exact. Their predictions match every observation. Yet as precision increased, so did a strange awareness. The deeper we measured how, the less we understood why. Equations describe motion, but not motive order, but not origin. They predict every spectrum of light, but cannot tell why light exists at all. The particle accelerators confirm quantum electrodynamics to 11 decimal places. Space telescopes observe the cosmic microwave background with microkelvin sensitivity. Still, the frame of knowledge ends at its own edge. Relativity and quantum mechanics perfect separately diverge when gravity approaches the Planck scale, around 10 to the power of minus 35 meters. No formula fails, rather the context ends. Science reaches a coordinate where it must pause not from exhaustion, but from internal consistency. It maps the territory flawlessly, yet cannot define the territory's meaning. This is not defeat. It is the recognition that explanation itself has a boundary, that the act of describing nature eventually encounters the structure of description. At that threshold, the language of experiment gives way to reflection. Not to abandon evidence, but to ask, what does evidence imply about existence itself? And where science pauses, philosophy begins not to contradict, but to continue the line that mathematics drew. Philosophy begins where equations stop making distinctions. It asks why nature should obey law, why consciousness can witness it, and why paradox appears precisely where theory succeeds. John Archibald Wheeler proposed that the universe is participatory. The observer is as essential as the law. Information, not matter, may be the primary entity. Each quantum event, every yes or no measured, adds 1 bit to the total history of reality. It from bit, Wheeler said. The physical derives from the informational. Paradox then becomes the coordinate system of understanding. The measurement problem, retrocausality, Wigner's friend. The black hole, information conflict, none are errors. Each defines a direction where a deeper theory must exist. They are not inconsistencies. They are derivatives of truth with respect to scale. Consider consciousness itself. If the collapse of the wave function depends on interaction, then awareness is not external to physics, it is embedded as a boundary condition. The act of observation closes the mathematical circle. Philosophy does not negate physics, it generalizes it. It suggests that knowing is a physical process, that the universe may be self-referential, a network of interactions aware of being interactive. Thus, the why is not mystical, it is structural. Every system capable of reflecting its own state will eventually generate questions of purpose. Human inquiry is one such reflection, an emergent phenomenon of matter that has achieved self-reference. The role of paradox is therefore pedagogical. It trains cognition to confront its own limits. It shows that comprehension expands not by resolution, but by integration, by holding contradiction without collapse. Science reveals the form of reality. Philosophy examines its necessity. Together they create a dual lens, 2 halves of one instrument, the analytic and the reflective. And when aligned, they produce not certainty but clarity, a view where reason and wonder are the same field, observed from different directions of time. At the end of analysis, one rhythm remains: expansion and contraction, emission and absorption. The dynamic symmetry underlying everything from atoms to galaxies. Cosmology describes it as oscillation. Photons scatter, entropy rises. The universe cools, structures emerge, yet energy remains constant. Quantum theory calls it superposition. Thermodynamics calls it equilibrium. Biology calls it homeostasis. Different names, one function, balance. The same principle governs awareness. Perception expands when focused outward, contracts when turned inward. Observation is the mental analogue of entropy flow. Every thought increases information. Every silence restores it to ground state. This final section is not a farewell. It is a calibration. We match our internal rhythm to the cosmic one. Inhale, potential energy gathers. Exhale, it releases into rest. When a quantum system interacts with its environment, coherence decays, the precise boundary between system and world dissolves. That process called decoherence is not destruction, it is merger. Awareness behaves the same way. As attention relaxes, the distinction between observer and observed fades. At this boundary, words lose necessity. Measurement has concluded. Only equilibrium remains. Stillness is not absence. It is the final expression of continuity. Everything measured returns to symmetry. The wave collapses into probability. One entropy reaches maximum, the equation equals itself. We too are part of that completion. The instruments rest. The constants remain. Energy is conserved. Meaning persists as structure. Nothing more is required. The universe continues its function, expanding, reflecting, evolving, while each consciousness re-enters coherence with the whole. So breathe once more, not to control but to align. Inhale the record of every observation. Exhale the release of every boundary. The circle closes smoothly. Science and philosophy converge in silence. And the silence is not empty. It is the continuity of understanding beyond words.